modern supermarkets, restocking shelves is repetitive, time-consuming, and physically demanding for workers. That's why our team designed the Colesworth Shelf Stacking Robot, an autonomous system that can navigate, identify items, and physically restock shelves safely and efficiently. The robot is made up of three core subsystems: navigation, vision, mobility, and item collection, which all work together to complete a full stacking operation. My name is Josh, and I developed the item collection subsystem, the part responsible for lifting and grouping items during placement. Our design used a 3-stage scissor lift powered by a NEMA 17 stepper motor and lead screw, paired with a servo-actuated 4-bar linkage gripper. This lift was chosen over a rotating arm or vertical slider for its compact footprint, stability, and smooth vertical motion. Two voltage converters, the MT3608 and LM2596S, step the 7.2 volt battery up to 12 volts for the stepper and down to 6 volts for the servo, ensuring reliable and efficient power distribution. The integration was done with 4 2mm screws in the base of the lift and directly placed into the chassis of the design. In testing, the lift reached the maximum height of the second shelf, unfortunately being unable to reach the third due to constraints. This can be fixed with an extra linkage in future designs. And the gripper, however, successfully did manage to grab all 6 3D modeled objects through full motion, confirming accuracy, stability, and repeatability for all of these operations.
Hi, I'm Saxon. I'm responsible for the mobility subsystem. To allow our robot to move, we've used a differential drive system with 2 independently powered rear wheels and 2 low-friction front support wheels. The powered wheels were driven by 2 50-to-1 micrometal motors. These motors were run via a motor driver hub, allowing a pulse width modulation signal to be fed to each motor, controlling the speed of each wheel. This allowed control over translational velocity and enabled the robot to rotate on the spot. The resulting robot has a maximum speed of 0.4 meters per second, allowing it to precisely move its 750 gram load.
My name is Oliver, and I developed the Vision subsystem. The Vision subsystem forms the foundation of the robot's perception and environmental awareness. The goal is to identify critical warehouse elements such as products, aisle markers, and picking stations in real time. To do this, the robot uses a Raspberry Pi camera HUD extension to run OpenCV and TensorFlow Lite, which are computer vision softwares built in Python. In this first image, we can see the original camera frame as it's captured by the Pi. From this, the robot begins processing the scene at around 10 frames per second. After applying a series of HSV color masks, such as orange for products and black for aisles and picking markers, the key features in the frame become amplified. These masks are then converted into a binary image so that only the relevant shapes remain visible for further analysis. Bounding boxes and range overlays are then applied. The bounding boxes identify each detected object, and the text displays its calculated distance from the camera. The type of product, along with its distance and bearing data, is shared with the navigation subsystem through an array to guide the robot through the warehouse to complete its tasks. Fortunately, an issue we ran into was that the robot could not distinguish between more than one picking station, which would prevent the robot from going to the correct station to pick up products. The robot can easily distinguish picking stations if it can see only one of the markers. And due to the aisle markers being separated by the 4 aisles, it had no issue detecting and getting the distance and range data for the nav system.
Hi, I'm Wilson, and I'm responsible for the navigation subsystem. The approach for this navigation subsystem uses a combination of state machine and potential field, both developed in Python. The state machine is the brain of navigation, and potential field its body. As the state machine receives range and bearing of markers, items, and obstacles from the vision subsystem, it gives potential field a goal position. The potential field then calculates the forward and rotational velocity, which can be converted into motor speeds. To travel between aisles and picking stations, the 2 shelf corners on the far ends of the middle line will be used to enable better positioning. The same machine takes on file and set target numbers, even shelf numbers on the right side of the aisle and odd shelf number on the left, and the bay number determines when to stop from the row marker. Here's a video to demonstrate. It is important to note that the current state of the navigation can only complete row 2, row 3's orders reliably. In the future, we'll fix the logic for row 1, integrates completely with vision, which also enables the obstacle avoidance feature to implement completely. Thank you.